All right. So my understanding is that the audience is more on the algebraic geometry side of the world. So with that in mind, I start there. So let me say what I think the torque variety is. Maybe before torque variety, let's say today. So projective space, I'm going to think of as Cn plus 1 minus 0 on C star. And more generally, torque variety is going to be Cn minus some locus I call C, non G, where G is some subgroup of C star G. Okay, so later on, we're going to have the usual discussion with cones and fans and so on. But for now, I would like to present my torque variety in this way. This is the kind of presentation you find in the paper of Cox. And the reason I would like to present the torque variety in this way is that it lets me calculate the category of coherent sheaves. Again. I guess I said out loud, but maybe I should say again, Z is a union of coordinate Hegler coordinate subsets. So if I want to calculate the category of coherent sheaves on this quotient, I guess I should, maybe it's best not to say variety. That. Ignore that. If I want to calculate the category in this quotient, well, each of these operations has a categorical translation. I take the category of coherent sheaves on Cn. I take the quotient by coherent sheaves on Z. It's important to observe that coherent sheaves on Z is not a subcategory. It's not a full subcategory of coherent sheaves on C. But I take its image. And then I take V inverse. Some words I'm going to say once and just never again. Always when I write coherent sheaves, I mean the unbounded derived category of incoherent sheaves or something like that, which you then, if you want to recover something more usual, you take compact objects. But it's irrelevant to the level of discussion I have here. And when I write something like this, I mean the homotopically appropriate notion. But that's important if you want to check for yourself that what I'm saying is true. But otherwise, you can just believe this. And what I would like to explain today is how to translate this across. So this is something which happens in the world of algebraic geometry. And I would like to translate it into something, this whole somehow discussion, which happens in symplectic geometry. that's what homological mirror symmetry is about. It's the assertion that somehow from symplectic geometry I should produce for you the same categories. Okay, that's what I'm saying. But so I wrote some notes for this talk, and there's kind of two steps that are involved in this translation. The first is turning symplectic geometry into a different subject called the microlocal theory of sheaves. And my original plan was to explain today first how the symplectic geometry turns into the microlocal sheaf theory, and then do this calculation. Unfortunately, when I wrote the notes for that talk, it was about 15 pages before I got to any calculations. So maybe I won't do it that way. Today, I will explain how to get some categories from microlocal sheaf theory that match this, and then next time I'll explain first how exactly that relates to the symplectic geometry, and then how to go beyond characterize. So it's not quite in the order I put it in the abstract, but that's okay. Okay, so that's the plan. And so let me now discuss what kind of sheaves, what kind of sheaves that I would use. I mean, one reason I'm going to do it in this order is that usually when I give this kind of talk, I start with the symplectic geometry, reduce it to the microlocal sheaf theory, say, okay, microlocal sheaf theory is easy, and then the talk is over. But yeah, this time, I'd like to explain a little bit about how to do calculations in microlocal. Okay, what sheaves? So I'm going to start with something much easier than this, which is maybe in the same world. You know, the simplest example of such a group G is just C star itself. And I'm going to think a bit about coherent sheaves on C star. Now, some kind of, what is this? This is some kind of modules over K, T, T inverse. And if I have a module over K, T, T inverse, that's just a vector space on which T acts invertibly. So from such a thing, I can make a locally constant sheaf on the circle. Okay, that vector space is its stop, and the way T acts is its monitor. So this is maybe the first instance of some kind of homological mirror symmetry. I explain next time why this is the same as the wrapped pi category of cotangent function. But that's for next time, so I erase it for now. And let me just say there's some instances of this correspondence. If I take, for example, a skyscraper sheaf at some point, what was the map? The map is I take this vector space, and I take an element of this as a module over this ring. I take the underlying vector space. I put that vector space at every point on the circle. But when you go around the circle, I identify it back with itself by the way T acts on the vector.
K is C, right?
Oh, yes. Okay. So one kind of element of this thing is C. So one element of this thing is the skyscraper sheet at some point, which is the same as the one-dimensional module on which T acts as multiplication by x. That's what that is. And so it goes to the locally constant sheaf, the rank 1 locally constant sheaf with monodromy x. Okay, that's one example. Well, let's give another example. Actually, maybe another example. Another example is I could take the structure sheet. And that corresponds to the module here, which is just C, T, inverse. And over here, it corresponds to something a little bit strange, which is the homological local system. And what that is if you take the map R as 1, and let's call this map something pi, and I take the constant sheaf on R, I can consider the push forward of the constant sheaf. Now this shriek means compactly supported push forward, and the reason it's the reason that the thing that corresponds to the compactly supported push forward is that I take polynomials here. And I'll leave you to think about that for yourself. This says the structure sheet for this one. This is kind of example. Then let me give the one more important thing to say about this correspondence, which is well, both. If you look at coherent sheaves on C star, you can tensor them, and if you look at local systems on S1, you can tensor them. But tensor does not go to tensor. Okay, so you can ask, what does tensor go to? And the answer is this correspondence that interchanges tensor product with convolution. Let me just do an example. So if I have two skyscrapers here, some O of x and O of y, 2 points x and y, I get rank 1 locally constant sheaves of monodromies x and y. And I get tensor them. And what I'll get is the rank 1 locally constant. So let me just write those as L x and L y. Those are the rank 1 locally constant. But if I tensor them, well, then the tensor is a functor, so the monodrome is multiplied. So this is L x y. And if I go back over here, what is that? That's O and x y. Which is certainly not the tensor product of these sheets. Okay, what actually is it? Well, what it actually is if I take, if I pull these both back to C star times C star, tensor them there, then I'll get the structure sheaf at point x comma y, and I can push forward by the multiplication method. And then I get this. And that's what this correspondence does. It sends tensor over there to convolution. Pull back, tensor, push forward. And in fact, it also sends, there's similarly a convolution over there, which gets sent to tensor over here, but I'm not going to use that today, so I won't. Okay, so this is the first example to think about if you want to think about this kind of mirror symmetry, and it's some kind of Fourier transform. It's a Fourier transform because it interchanges product and convolution. That's why people call it Fourier transform. Okay. So that was the first example. Now, second example. I want to now find something that has to do with coherent sheaves on C. And so we'll get there in a bit, but that's we're going to have to go on some kind of digression because locally constant sheaves aren't going to do it for us. So now I'm going to discuss the micro-support sections. First of all, what is the and just to make sure, in case you don't know what a sheaf is something which every open set assigns a vector space, a module or something like that. And then when you shrink the open set, you get maps between the module and the vector space. So let me just write that down. What is a sheaf? A sheaf is something on some topological space, which when you have an open set, is called F. And M is the kind of thing when you have U inside V, V inside U inside M, then F assigns U, F assigns something to V, and there's a map. And that's all that I need to know to tell you what micro-support is. So if you have F on M, the micro-support, which is called, written like this, is a locus in the cotangent bundle. So now M is a boundary. It has a cotangent bundle, and the micro-support will be something inside. And it's going to be something tonic. You'll see that from its definition. What is it? Well, for each covector in the cotangent bundle, I should tell you when is it in the micro-support. So let's just draw a picture.
Micro-support and singular support in the same thing?
And that's a long story. So originally, singular support, if you look in the old papers of analysis, had to do with when you had a distribution and you ask yourself where in the base is that, where on M is that distribution not a function. And so in fact, the word singular support meant something in M. And then there was something else called the singular spectrum, which was the locus in the cotangent bundle in the directions in which your distribution was not a function. And that's why this is called SS. So originally it was for singular spectrum. I think that distinction has become lost with it. However, then, I mean, this is not, I mean, this is a sheet, it's not like a function. And so in the next step is then people study the D modules or whatever, and observe that the characteristic cycle of the D module controls the singular spectrum of its solutions. And this is most like the characteristic cycle. That's how you should, I mean, that's what okay. I mean, in particular, when F is the sheaf of solutions of a D module, this is the characteristic cycle. It's not a cycle, but the characteristic cycle lives on this. Okay, but let me just tell you when something is in the, like what it is. So I have a covector. And this covector lets me draw some kind of half disk. And the one thing which a sheaf does is, well, I'm allowed to compare half of the whole disk to half of the half. That's when I have conclusions, I have a restriction map, and I can ask, is this map an isomorphism? And if the answer is no, then this covector is in the microscope. So that's what the microscope is. I'll do some actual examples in a second. Also, I mean, this is what you do when the vector is not a zero vector. Inside the zero section, the microsupport is just the support. But usually we won't be concerned with things in the zero section. Okay, so that's the definition of the microsupport.
Are you ever going to look at these things if the sheaf is not constructible?
But typically, the sheaves of interest today will always be constructible. Let me answer this question responsibly. So typically, if you read Joshua Speer, into the word constructible is built the assumption that the stratification that you work with is subanalytic. And that condition is okay for most purposes, but when you're doing symplectic geometry, it's not so. And so sometimes when you want to discuss things, you don't want to say the word constructible. Instead, like for example, I'll mention this, the natural analog of constructible, which is more or less equivalent, is that the microsupport is Lagrangian. But you can say that without saying subanalytic. So that's why everything today will be constructible, but there's another hypothesis which goes into constructibility sometimes. I mean, some people think constructible means perfect stocks. And I never assume that. So that was some kind of digression. Okay.
Sorry, Vivek, do you assume that this open set is like small around like each point?
Yeah, I should have said if I have x, c, and p star f, and I want to know is x, c in the microsupport, then I take a small open set around x, I look at the codirection of c. In fact, you have to even be, this is a bit heuristic what I said, you have to write the definition a bit more clearly. The definition is obvious. Okay, so I want to do some honest examples. And the smallest manifold I can make is the real line. And so I'm going to discuss some sheaves on the real line. I'll talk about two of them. I'll take the constant sheaf on the half open interval to infinity, and the open interval to infinity, and the constant sheaf on the half open interval. Yeah, and what is the difference between these two sheaves? What are these sheaves? Well, let me do the colors. So this one will be in this color. And this one, there's point 0. This sheaf is the sheaf where if I take any open set on this side, sections over there is just z. Any open set on this side, sections is 0. And an open set which contains 0, sections is 0. Okay. So now if we think about these restriction maps, well, the restriction map in this direction is not an isomorphism, and the restriction map in this direction is an isomorphism. And so that means that if my original covector was this way, then that restriction I drew was not an isomorphism, so that covector is the microsupport, and the other covector is not. And it's easy to see that away from 0, all the covectors are not. So the microsupport of this guy looks like this, and I leave you, and maybe, and this other one, this one, well, it has the other thing. It has z when, for that one, this thing gets assigned z, this thing gets assigned 0, and this one gets assigned z. And so that one has the other thing here. Its microsupport looks like this. Okay? Maybe somehow it looks like this inside. Like, here's the whole program. There's the whole program. That's the.
Like, sorry, in the strictly positive part, shouldn't the microsupport be the whole vertical line?
No. Can you hear?
Well, in both examples.
So the reason it's not the whole line is that the restriction in one direction is not an isomorphism, but the restriction in the other direction is an isomorphism. And you see, this was direction. So like when I took the positive covector here, then I compare this whole one to this side. Whereas I could, and so here that is an isomorphism, so the positive covector is not included. But when I take a negative covector, then I compare this thing to this stuff. And so the negative, and that's not an isomorphism, so the negative covector is included.
But like, for example, over point 1, I can choose a small disk so that the restriction in both directions is an isomorphism.
But point 1.
Yeah.
Going away from 0.
Yes.
Yes, and that means nothing is
Nothing is in the support.
in the support.
Ah.
Except along the 0 section where I include it because this supported issue.
Okay.
Yeah, it's the opposite is what you're doing.
Ah, okay. Thank you.
Okay.
So, when you draw the restriction from a disk to a half disk, the half disk is open?
Open. Okay. Like I said, this definition is good enough for any calculation I'll make here. The actual definition takes like half a page because you have to work a Cantor set. Okay. So that's some kind of example. Then I want now to go to maybe the next most complicated manifold, which is S1. So look at S1. Circle. And I'm going to draw the circle as just a line, but you have to glue up the ends. And let's consider sheaves on the circle whose microsupport looks like this. You can ask, how would you ever produce such a sheaf? Because, maybe you try and produce one where say, okay, well, I know, I have a good idea of what to do maybe at the beginning. Okay, because this sheaf looks like that. So I take a sheaf which is which is non-zero, including at this point, and starts going. Then it's continuing, and now, okay, now what? There's two things you can do. One is you can just keep going. Okay, that's one part. Just keep going forever. And so, what is that? That's the push forward from R to S1 of this sheaf along the natural path. Okay, that's one option. The other option you have is you can, other option you have is you can do this. You can take the sheaf that starts going and continues, and then somehow, but there's no meaning to the height of these lines. Okay? And then does not include that. So this is like the push forward. So we don't have R to S1. This is like the push forward of, it doesn't matter if I use star or street for this complex code 1, of the constant sheaf on like 0 to 2 top, like this. Okay, so that's this right. And that's another thing which has the right problem. So it's a lot like what?
It seems like it has multiplicity too.
Yeah. So what is the micro? I didn't put a number. You're right. This one, if I were to draw its characteristic cycle, I would have to draw it like this. But I'm just looking at microsploited in this set. Actually, you're right and you're wrong. Okay? If I drew its characteristic cycle, it would have multiplicity 0. Those two would actually cancel. And maybe the way to think of this object in terms of local systems on S1 And this will make maybe more sense next time when I explain it, when I discuss the category and so on. Is you should think of this as a local system where the monodromy has developed a singularity at this point. The monodromy has gone off either infinity or zero or something. Good? You don't want to think about it in a way you don't have to. It's just that. Okay, so that's some examples. And now I'm going to give you an exercise. I'm not going to do this exercise, but you can do it. The exercise is that sheaves on S1, which are microsupported in this funny picture. So here I just indicate what the microsuport is supposed to be. It means this. This is equivalent, this category is equivalent to the category of coherent sheaves. And it's an equivalent, it means some of these, the local systems on S1, the local systems on S1 are just the sheaves with no microsploit outside the zero section. And that's included in here, and this is compatible with let me not be too picky about how you turn a coherent sheaf on C star. You should be a little bit worried about this because if I push forward a coherent sheaf on C star, it's not coherent anymore. But like I said, I take some kind of incompletion of these categories until I ignore this. Okay. So I leave this as an exercise because that's one you can do yourself, and I'm going to use that as some kind of building block for the rest of it. And basically what I want to explain here is that once you know how to deal with the circle, you can deal with all of them.
Can I also consider sheaves with like microsupport like this? In the circle, like circle and
Yeah.
several. What will this be?
So if you did, let me go out like this. There's two different things you might need, so I'm going to do them separately. In fact, it'll be a consequence of what I explained now. You might mean this. And you might mean this. Okay? And it turns out these are different things. This one, it turns out, is A1 mod B mod 2, plus minus 1. And this one is B.
Are they using different spaces?
No, I haven't told you that. Just like if you were to compute the category of sheaves, it would be the category of sheaves on those spaces. The category of coherent sheaves.
But the punchline is it's always going to be toric. And you're going to tell us what the toric thing is.
Not for any arbitrary space, but if you take S1 and you do this.
Yeah, if you do a torus, for example.
So let me explain what I was explaining. Okay. There's a couple more facts that I'm going to have to take as some kind of input into this machinery, which is that this relationship of including these sheaves in here, well, I can also tensor something on here with a local system, and I won't change its microsupport because I'm just tensoring with something invertible everywhere. And I can pull back something in here by C star action, and you can check that this isomorphism defines those actions. And the other thing which I'll need to know is that when you remember I said something is in the microsupport here if some cone, if some map is not an isomorphism. I could take the cone of that map. And that would be some vector space. So for any sheaf F on S1, I could take the cone of this restriction map. And that's called the microstock. Microstock is home of the So the microstock vanishes if there's no micro support there. But there's also a map from the sheaf to its microstock. And the other thing that you have to check for yourself is that if I take the microstock, I'll just note that on U. And if I take here the restriction at 0. Restriction 0. Well, these both map to the category of vector spaces. That. And this diagram. Okay, that's another thing that we should check. Kind of fact about this. Okay, so that's those are the facts about. The way to say what facts I've just told you. This is equivariant symmetry for the affine. That's what I've just told you to assume, or that you can compute it for yourself if you want. I haven't yet told you what it has to do with symplectic geometry, but that's what that is. And now I'd like to explain, the point of this talk is to explain how equivariant symmetry for the affine line implies symmetry for all point products.
So how do you get things like Q1 so working with the affine line?
I will show you. I mean, remember, P1 was some quotient, of some deletion. And I'm going to explain now what is the mirror construction to deleting and taking a quotient. Well, the first thing I want to observe is that both sides, I mean, I'm good at taking sheaves, so both sides commute with taking sides. Okay, so sheaves on the nth power of this thing on S1 to the n, well, that is equivariant sheaves. And that's just knowing enough about Kunith on everything in sight. Then let me give you a better picture of this for n equals 2. Well, the way you for n equals 2, I just want to draw what is this thing squared. Okay? So I'm going to here is a picture of S1 times S1. It's the torus, which is both the ends. And the way you draw these conormals is, well, you can have a conormal times the zero section. That's the conormal to this line. You can have in the other direction a conormal times the zero section. That's the conormal to this line. And you can have the conormal times the conormal, and that's the whole conormal to this point. Okay. So that's what is this thing squared. That's how you draw.
What about leaving sheaves that are non-tonic?
So the point is that this thing is O A1 tensor. And here you have to take in and take Leary tensor product, whatever. Tensor A1. And the other
So
side
if you have
also.
an elliptic curve in the plane, what do you get?
I mean, resolve it by sheaves and send the resolutions over. Maybe a simpler, how to say, like one dimension down, you're asking if I have a point that is not 0 in A1, what is it? And a point that's not 0, that was a local system.
I can deal with points, but
Okay.
when you have high dimensions,
I mean, not every element of the tensor product is like,
Decomposable.
yeah, it's decomposable. I mean, you know, if you want elliptic curve or whatever, you write that as a map. You resolve it. Some map from O to O. And well, column OO here is the same as column OO there. So I only have to tell you what O is.
Sorry, shouldn't it be like a corner at the point? Yeah, so like we have half line and half line.
Oh yeah, sorry, I did it wrong.
Like,
There you go. Okay. We're good. And now I tell you, first I'm going to tell you, remember toric variety, I've gotten out to Koya. On toric variety, it was going to be an minus something mod something. And so first let me explain how to delete something. So Z and an union of hyperplanes of linear symmetry. Now I should take the quotient by the image of coherent sheaves on Z. But and then that's the same. That's the same as doing it for each linear subspace separately. So let me just take a little, let's discuss for the moment one linear subspace. And linear subspace, well, sorry, I didn't mean linear subspace, it's a coordinate subspace. Coordinate. A coordinate subspace is a product of 0 in some factors and the line in the other ones. So restriction to a coordinate subspace is going to be a product of this, like taking the microstalk along some of the factors. And so if you translate that to this product, the restriction an to ak, where k is some particular top three factors, is microstalk given by it's called microlocalization. Along conormal to the corresponding hyperplane. Because here it was somehow with this microstalk. Okay, so how do I take the quotient? Well, I want to know that it impose that this be 0, which means that this restriction be 0, which means that I impose there's no microstalks on those coordinate numbers. So the long and short of it is that deleting this coordinate subspace is the same as removing corresponding conormal in this picture. And let me just do an example. I mean, you won't see, it will not be evident from when I draw that that statement is correct, but just so you see what is meant. Already here. So here is A2, and if I wanted it to be A2 minus 0, as I might want to get P1, I'm supposed to delete the corresponding. This is now supposed to be A2. So that's the first step which you should do. And then let me talk now about the quotient. Okay, so here you have to think about it. So she's on S1. Let's go back to some kind of easy example. She's on S1 and she's on. Let's discuss what is the relationship between these two categories. And there's two relationships between these two categories. The first one is an easy relation. Sheaves on S1 are the Z periodic sheaves on R. That's like some kind of descent fact. But there's a less obvious fact, which is that if I want to recover sheaves on R from sheaves on S1, well, remember I told you that the multiplicative group acts by somehow a point in the multiplicative group tensors by that line. And if you think about it, that action, it comes from somehow the monodromy. That if there was no fundamental group to be had, there would be no room for me to act by a representation of the monodromy. So you might imagine that if I trivialize that action, if I take the fixed points for the GM action here, then that should be the same as forcing the fundamental group to be trivial. Okay, so you might imagine and in fact, this is true. And it's true by an argument I won't explain, but it follows from Gauge squares 1 F1. But the reason you should think it's true is that this action somehow knows everything there is to know about the fundamental group S1. And so by killing it, I demand that you pass through your original. And that's why you should think it's true. Well, you might also think of this as some kind of categorical version of contradictory. Okay. So now I'm going to explain how this kind of business lets me take the mirror of taking equation.
Do you have any other examples of that kind of invariant application experience?
I mean, it's what people call, it's very close to what people call this equivariantization, de-equivariantization correspondence, like you find in, I think, what one place it happens is in this Bezhekovnikov's two geometric constructions that happen in algebra. But it's not quite, I mean, how to say, you don't have to say it. Anyway, it's more or less that.
Do you use it for local systems a lot? It's okay. I'll look up.
Oh.
Yeah, great. Thank you.
I like to say, the way I learned about this gauge squares 1 half on this is I thought this fact should be true, and I asked some people how to prove it, and Justin Hilbert and Nick Rosenblum told me use gauge squares 1. So if you really want to know, you can ask this. Okay, so back to this beginning setting, we have this an minus z on g, where g is some subgroup. So I'm going to write g on now. G on. And I'm going to write an, so it's cn. And we have, so let me just write somehow. This character is, so T is the torus that acts on the toric variety. But I'm going to write the characters of these things. So now it is just I take om into C star, om into Tn. The characters of these things is Tn. Okay. And when I use those is that I take the, I have this lambda z I'm to write for the thing I get by deleting the pieces corresponding to z. And that one is lived in T star Rn mod Zn. And I want to go up to something I'm going to call lambda Zn, which is just the cover of this one that I get from pulling back along the natural map to Rm. So I'm going to go up to this cover. And I'm going to go back there and do an example in a second, but let me just say this kind of thing. And now the point is that by the same kind of yoga of invariance, covariance that I said before, well, we had already seen that sheaves lambda z lambda z lambda z or n mod z n. What we already saw that this thing is co n mod z or minus z. Okay, that's what we saw before. And now I'm going to apply. I'm going to first go up to this cover, right? Lambda zm, m, and then apply descent. So this is just like the statement that z periodic sheaves on R were the same as sheaves on S1. That's all I did here. I went up to a cover and I demanded that things should be periodic. Okay, so this is now still true because I didn't change that category. And now I take G invariance on both sides. So I take G invariance here. Okay, good, that's what I wanted. And I take G invariance here. But what does taking G invariance here do? Well, Zn mod m is the character lattice of G. And so by that same thing with Z and C star I did before, taking G invariance here kills this. So there you go. This category of sheaves is coherent sheaves on the toric frame. I'm not quite done yet, and the reason I'm not quite done is that this provides some kind of incarnation of that category of coherent sheaves, but it's not a very satisfying. And the reason it's not such a satisfying one will be apparent if I look over here.
Yes, so you remove the Zn mod n invariance condition, and what did you put instead?
Well, okay, let me just do it again. So I have Zn mod n invariance at the moment. Yeah. And this was the fact we knew before. And I'm going to take G invariance on both sides. And well, G invariance on here is just G invariance. Now here, that like Pontryagin duality business, they cancel. Because this is precisely as characterized.
Mhm.
So let me go over here to this example and say what just happened. Okay, so what happened here is when I take the quotient by C star, that corresponds to unrolling this torus in one of the directions, kind of like in a diagonal direction. And so what does that look like now? So now I have this kind of tube, kind of cylinder, and I'm not sure I'm going to draw it exactly correctly, but it goes something like this. So now this comes on the back of the cylinder, on the front of the cylinder again, on the back of the cylinder, and the front of the cylinder again. And it just kind of like continues like that forever, periodically. So I drew a bad canvas look. I tried to draw a three-dimensional picture of a cylinder, but let me just instead say I drew this side and this side. And then it looks like this. And the fact that I proved to you so far is that sheaves on this long cylinder with this microsport condition is co-P1. So now we're down to P1. But the reason you should not be satisfied with that is that co-A1, well, co-A1, that was supposed to be sheaves on S1 with this microsploit condition, and that's one dimension. And in particular, its cotangent bundle is the same real dimension as A1 was, whereas this is bigger, and that's not great. And the solution to that is the following. So I've run a bit out of time, so I'm just going to tell you what the solution is. I'm going to pick up next time about saying a little bit more about the solution. The solution is that, well, now that I've unrolled it in this direction, it comes with a projection to M order. This is literally Rn mod M, and so it projects to Rn mod M tensor. Okay, it projects to that. And we just take a fiber. Okay? And what I haven't explained to you, which is maybe actually the most interesting part of the argument, is why taking a fiber preserves the category. But that actually involves some symplectic geometry, so I'll explain it in part of the next time. I'll explain some other things about before I explain that. But let me just draw the picture if you want. What do you get when you do that? Well, the answer is this thing that I drew for Scott before, which is that you get something like this. That's what happens. And actually, an interesting thing which happens is as you move this slice, you get like a local system of categories that somehow is constant. And what happens is these things wind around and around the place. Okay, and time is finished, but let me. So I'll state next time the combinatorial description of what the result is. Like how to describe the result. But let me say, I should have said this at the beginning, that this is what I consider to be a shorter, not that short, a shorter proof of a result which is known and is originally due to somehow some complicated series of people. It was Bondel, Fang, Yu, Herman, Saslow, and then Kozaki, also Dmitry Venturov, and Kanigov. So these people, and many other people all worked on this, and I think these three people finally gave the final proofs of it. They gave three different proofs, and this is yet another proof. Okay, well, I have to stop now, but we'll continue next time. And next time, I'll explain a bit more about how. So today, you see this kind of manipulation that I'm doing, even if you didn't exactly follow why I was doing it or why it was allowed and so on, that sheet theory is easy to work with. And then tomorrow, I translate it into, next time, into statements about the Sky category, which is not as easy. Okay.
Thanks, Vivek. So nowhere here actually you assume that G is connected and it doesn't play any role.
I didn't assume G is connected. And in fact, you can't. I mean, some torque varieties you need G not to. There is something which I assume, this very last bit about taking the slice. I assume nothing about anything until this last bit about taking the slice.
Mm-hmm.
And taking the slice, that only gives you an equivalence when the torque variety is simplicial. Or in other words, only when that quotient is Riemann percent. And there's an interesting reason for that, which I'll explain next time. That's where you see some actual symplectic geometry. In the reason why this is an equivalence.
But if you take the big model, it's still going to be an equivalence.
Yeah, this big model is an equivalence. And actually, there should be, I mean, there should be something interesting which happens when you think about what is going on when that's not a delete Mumford stack, and you take this slice and move this slice around, or different slices have different
Well,
behavior.
there will be a monodrome reaction on the stabilizers.
I don't know what there will be, but yeah, maybe. But
No, some digiting has to come out because, you know, if you have continuous stabilizers, there will be a non-trivial monodrome reaction which is not coming from the fundamental group, it's coming from, you'll need a derived structure on the base in order
But also there's another, I mean, it is not locally constant,
Right.
these slices, in particular. So like some of those slices will be more interesting than others. And I don't actually understand what is going on with this group.
I find it hard to understand how a slice of that gives us this picture.
Well, you are asking why.
The starting
Well,
point,
okay, first of all, the slice is a circle. So that's good. And maybe you're asking why one points up and one points down there instead of both pointing up. And the way to think about it is that this is pointing kind of outwards, and this is pointing kind of outwards. And so when maybe better to wiggle this a little bit.
Well, one is in front and the other is in the back of
Yeah,
the split? Oh, sorry, I saw that.
It's because I mean it's like this, and the point is that when you restrict it here, it points outwards, and this one also points outwards. But outwards here is the positive way, and here is the negative way.
So I think I saw that, and I didn't say three-dimensionality, but I guess I just, thank you.
the fundamental domain is two of these squared, right?
How many exactly is that? I don't know, but yeah, maybe.
Well, I mean, yeah, each of these squares is one half, two adjacent squares exactly be different.
That sounds right.
And that's where you get the Tucano ones, by pointing out the direction.
Okay.
Okay, well, thank you, Vivek, and we'll continue on Thursday.